Today is March 6, 2023, and we're starting chapter 20. The first thing you have to know is electromotive force. Sources of electromotive force is a source of electrical power. The word force here is a misnomer. Okay, it's better if you call it a source of electromotive energy. Batteries are source of electromotive energy or electromotive force because they provide energy out of that potential difference that you have. Okay, and batteries are an example of a source of electromotive force because they have an electric potential that can be used to make electric charge move. Okay. Once you have a force of electromotive force, you can get electric charge moving in a circuit. Circuits in general are made electric circuits in general are made from conductors. That's why we have the copper wiring at home. It could have been any other metal, okay, but we use copper because it's cheaper. Could have been not just copper wiring, but it could have been gold wiring, but it would be too expensive. Not only would be too expensive, but gold wiring is not as conductive as copper. Okay, one of the best conducting materials that you're going to find out there is silver. We could have, instead of copper wiring in our homes, we could have silver wiring in our homes, but again, would be too expensive. It's a better conductor than copper wiring, but it's more expensive than copper. Copper is among the top conductors out there that we see. And because of the cost of copper compared to other metals, we use copper extensively in the circuits that we have at home. That's why copper is one of our best conductors after silver. We can even go check the internet here. Conductivity of metals. Conductivity of metals. Okay, here you go. We have it. Electrical resistivity and conductivity, Wikipedia. Okay, let's see a table here. You don't want to see that. We don't have a table here today. Okay, here you go. We have it. Okay. Conductivity. Look at the conductivity of silver. Look at the conductivity of copper. And then we have annealed copper that's a little bit less conductive than regular copper. Another way of measuring conductivity is what we call resistivity. The higher resistivity, the less conductive the metal is. So you can see that copper has a higher resistivity than silver, right? What does it mean? It means that the conductivity of silver is higher than that of copper. And have all those metal. Gold, look at the conductivity of gold. Conductivity of gold is half, almost, no, it's not half, 50% less, right, than that of copper. 20% less of copper, 50%, yeah, 20%, 20 to 30% less of that copper. And then aluminum is not a very good conductor compared to copper, brass, calcium, and so on. So we are very fortunate that copper has a very good conductivity and is also so cheap and abundant as well. We're very fortunate. Okay, going, the conductivity here is decreasing, right? That's in order of conductivity. You can see that carbon, graphite, seawater. Look at the conductivity now of seawater, 4.8, 7 orders of magnitude lower than silver or copper. Okay, drinking water, oh, even lower. Seawater is more conductive than drinking water. Seawater is more conductive than drinking water because we have salt there dissolved. Anything that has ions dissolved make the material, make the liquid more conductive. Okay, and then the other spectrum right here we have Teflon. This is a dielectric material, fused quartz, a dielectric material, wood, air. Look at the conductivity, 10 to minus 15, much lower than that of copper and silver. Going back here. All right. To understand how electric charges move in a circuit made of conductors, okay, we have to look back at our course, at our chemistry courses, okay? Specifically, how atoms are put together, how metal atoms are put together. At this point in time, everybody has that very good picture of an atom, right? It's a nucleus, a very small nucleus with electrons moving around the atom. That's a very good picture to have of an atom. Not only we have positive charges here in the nucleus, but we also have neutral charges in the nucleus. The nucleus is very small compared to the orbit of those electrons. Now you have to remember that we have those valence electrons in atoms. The valence electrons are the ones that are in the outer shell of the atom. Okay, so let's write that down. So, recall how the atom is put together. We have a very small nucleus that is positively charged. It has protons and neutrons and several electrons orbiting the nucleus. The electrons that are furthest away from the atom are the valence electrons. Why they are important? They're important for the following reason. They are important because they are weakly bound to the atom. Anything that you do, that valence electrons may escape the atom and go elsewhere. Okay? Anything you do allow these electrons to move away from its original atom. Okay, they are important. And the picture that you have to have in mind, again, is this one here. Here, let's say it's my valence electrons. Now, when you put all those atoms together, like in a bar of iron or in a wire of copper, you're going to have all those the nucleus of those atoms together like that. Okay. And don't forget that I didn't draw the electrons moving around the nucleus here. Okay. And when you have a situation like that, we say that the metal is in a crystal state. Okay. The valence electrons, they jump, they keep on jumping from one atom to another. That's a characteristic of the valence electrons. Okay. I'm gonna put it here. Here you go. That's the negative charge jumping from one atom to another. That's another negative charge. That's another negative charge, and so on. So those valence electrons are capable of doing just that. When you have a piece of copper, a piece of wire, a piece of iron, silver. Okay. And it is those valence electrons that are responsible for the electric current in the atom, okay? In the wire. Not the atom, but the wire. Here you go. Here is a little drawing of my circuit. Here is my copper wire that I've blown up. I'm using a very strong microscope that can see what's happening in this atom. In this bar, I connected this piece of metal to an electromotive force, to a battery. Okay. And this battery is the positive side of this battery attracts the negative electrons, generating a current here in this device. Make sense? Okay. So let's I'm gonna write that down. Okay. When we connect a metal wire to a source of electromotive force, a battery, for instance, this source has the ability to provide, this source has the ability to power the valence electrons in the metal, producing a motion in a single direction. Okay. So the first idea, right? Let's just summarize, right? What you have to know about electric charges, right? We have been talking about that. We know about should know about electric forces, just to visualize the invisible. What is invisible? It's a very good model, this one that I'm discussing with you. It's not exactly what we have in real life, but it's still a very good model. Later on, you're going to find out that it's not exactly that. But this, what we call this theory that I'm explaining to you, is a first order, I would say a second order approximation, even better, it's a second order approximation. Later on in graduate school, you're going to learn the third and fourth order approximation. You have an electric force, you have an electric potential, right? Batteries are source of electric potential. And now you have an electric circuit. So let me, going back here. The story goes like that. The positive side of the battery attracts the electron. If instead of having a battery, you would have a capacitor here instead. The capacitor would lose charge little by little because the negative charge is combined with the positive, okay? But because we have a battery is a slightly different beast. It's a slightly different device. It does have a positive side and a negative side, but it has something else too. It has a chemical power plant between those two terminals that has enough energy to separate the negative charges from the positive charges. That's what the battery is. And that's how different the battery is from the capacitor. At principle, they look similar, but yeah, to a certain point, they are similar because they have positive and negative electrodes. But then the battery is more than a capacitor. The battery is capable of separating the negative charges from the positive charges. Capacitors cannot do that. That's why they become discharged. They eventually become discharged and you have to charge them again. I have this picture. Okay, so the picture goes like that. In an electric circuit, the battery makes the electrons move towards its positive terminal. Okay. When the electrons reach the positive terminal, reach the battery's positive terminal, right? Battery's positive terminal. It has enough energy, I would say enough chemical energy, I'm gonna put it this way, chemical energy to separate the negative charges from the positive ones. And it's because of this energy that the circuits keep on flowing for a rather large amount of time. Okay, depending on the amount of current that you're powering in your circuit, batteries, 9-volt batteries can last, let's say, 12 hours. And if you go in your battery, that's an interesting thing too. If you go in your battery, many batteries, that's how much, the manufacturer, they print on the battery how much energy it has. Let me see, this one has it. Yeah. How much, not how many energy, but how much charge it has. Let me stop sharing my screen so you can see it. Here's my battery. There's a 1.5 volt cell. Okay, here you go. Yeah, do you see here? AA, right? This is a rechargeable battery, by the way. I only use a rechargeable battery. I don't like to buy the other types of batteries. 2,600, and then I'm going to explain to you what this thing here, this unit means, okay? Milliamp hour. Okay? Milliamp hour is a unit of charge, coulombs. Okay, you can reduce this milliamp hour to coulombs.
And so that's what it says under the 2,600, right? Okay.
Yeah, I don't think I can get it focused there, but it says milliamp hour.
Okay.
Okay, but you can see the 2,600, right?
Yes.
Yeah, you can get any battery, you're going to see something like that. Okay, let's see, maybe I should come closer and closer. Yeah, it's not focusing, unfortunately. But you believe me, right? I'm gonna write that down there in my, and that's where we start talking about current. Okay, some batteries out there have a charge of 2,600 milliamp hour.
We can't see your screen.
Oh yeah, let me go back. Thank you.
Yes.
Equal 2000, which is equal to 2.6 amp hour. Well, I'm going to talk about amp very soon here, what amp means. Right? Milli is 10 to minus 3, right? 10 to minus 3 times 2,600 is 2.6. Let me see another battery that I have here. I have another one, the Duracell. This one doesn't have, this one doesn't have the amount of charge it has, unfortunately. Sometimes they print it, sometimes they don't print it. Yeah, my Duracell does. I have only the voltage here, unfortunately. But those 9-volt batteries has more charge than the. And then whenever you're performing an experiment, you know, if you know the amperage of your circuit, you can choose a proper battery that's going to power your circuit for a given amount of time. I used to do that in an experiment that I would deploy my sensors in the field. Okay, I knew that my 9-volt battery had a given amount of charge, and I knew how much current, right, my circuit would consume. I would do some math, and I would find out how long my battery would last. It usually would last like 9-10 hours with my circuit. So I would wait 9-10 hours. I'll go back to the field, I'll change the battery, things like that. So now that we're talking about motion of the electric charge, we can start talking about the current. Okay. And the unit of current is the amp. Here you go. We have a copper wire, right? We have the valence electrons. I'm not depicting the positive charges. And by the way, something very important that I didn't tell you. Only the valence electrons move, and there is a very good reason for that. The nucleus do not move. Okay, the nucleus do not move, even though you're applying a force, an electric force to those charges. The nucleus that do not move for two good reasons. One, the nucleus is far heavier than an electron. Remember, the mass of the nucleus is 1,800 times more than that of an electron. Okay. You need a much higher force, much larger force to make those nucleus move in the crystal lattice of your metal. That's one reason. The second reason is that all those nucleus, they are bound to each other in a very strong lattice, and every other electron, with the exception of the valence electrons, also stays with that atom. So even though we are applying an electric force to this piece of copper, those nucleus are not going to go anywhere, because the nucleus are much heavier than an electron, and on the top of that, the nucleus is fixed into place, bound by forces between them. Okay, and the other electrons, they are far more confined here inside, nearby the nucleus. The electrostatic force is much stronger also than the electric force provided by this battery. Okay. Here you go. And the battery, it has enough. Okay, good. Okay, this produces an electrical circuit where the valence electrons are like cars, right? Moving in their circuit. So the valence electrons come here to the positive plate, attracted by the electrostatic force. The chemical power plant in the battery that we have right here has enough energy to separate the negative from the positive charges. Once the electrons go to the negative plate, now the negatively charged plate repel the valence electrons that continue moving here in the circuit, you know, until all the energy here in this battery is spent. until all the energy of this battery is spent. That's the picture that you must have. So that's it. Here you go. I'm going to give you another picture. Here are my valence electrons all over the copper cable. We put together a battery, let's say 10 volts, a 10-volt battery. The positive, here you go. Here's another way to understand what happens, okay? Another way to understand what happens. This battery, not only it exerts an electrostatic force, but it also creates an electric field inside this copper wire. It creates an electric field, and the electric field is pretty, is very much constant, uniform. Very much uniform. People have calculated that and they have found it. It's not easy to prove that mathematically. And now that you have this electric field, the negative charges tends to move to the positive side of the electric field, right? To the tail side of the electric field. And it is as though if we had positive charges here at the end of the copper wire. Did you notice that I dashed the electric field? It is as though as we had positive charges at the end of my wire. Okay, and then the electrons start moving. This motion is called electric current. By the same token that we have water current, which is the motion of water. Water moves in a channel, for instance, right? We also have an electric current, which is the motion of electrons in a wire. And now, how do we measure this electric current? Okay. Here's the mathematical definition for the electric current. We get a wire. We imagine a gate right here, a circular gate that is the same cross section of your wire. And suppose that you have your little green man here that's observing those electrons going by this gate, and he keep on counting how many charges are passing by in a given amount of time. The amount of charge divided by the amount of time is the current. Is the current in the circuit. Okay. So definition, right? The very important concept. It's so important that some books consider the current to be the basic quantity in electricity, not the electric charge. Okay. Some books state, look, it's not the electric charge at the basic quantity, but it's the current. And there's a practical reason for that. Okay. There's a practical reason for that. And the practical reason is that it's much more easier to measure an electric current than to measure an electric charge. Okay? It's much more easier. So, definition of electric current. The amount of charge that crosses a given cross section, we say that we call it a cross section of a wire in a given amount of time. In a given amount of time. The strict mathematical definition is what you saw that in that slide. I is delta Q over delta T. Since it is the electrons that are the source of current in most circuits, not every circuit, but most circuits, we can here write this formula in the following way. Is the number of electrons times the electric charge of the electron. That's what delta Q is. Ne over delta T. That's what you have in there. Important definition. 20.
Professor.
Yeah.
So when we're thinking about the movement of the electrical current, like visualizing it, would it be accurate to visualize it as if we were visualizing the like running water in a river?
Yeah, exactly. The droplets of water is a current of water, right?
Yeah.
So that's the same idea, right? You may have
Yeah.
current of electrons, you can have a current of water, you can have a current of balls, right? You can. Current is a very generic idea, right? It's a very generic idea. It doesn't have to be a current. It doesn't necessarily have to be a current of water. It can be a current of whatever you are using to move. A current of cars in a freeway.
Right.
Have you thought about that? Right?
Yeah. Okay.
Number of cars that pass a given section of the freeway. You count the number of cars and the amount of time. It's the same idea, but with different, right? With different, how do you say? Different players here, different particles, different objects. Okay. Now we're going to talk about the unit of current. Didn't do it. Interesting. Let's try it. The unit of current is what? Is the unit. Okay, now we did it. Is the unit of electric charge divided by the unit of time. Here we're doing our dimensional analysis. The unit of charge, you already know, is the coulombs. And the unit of time, you already know, it is the delta T. Right? This unit shows up so frequently in physics that we call it the amp. Amperes. Okay, or amp, or A. And that was the charge, and the charge of my battery, right, was what you saw here. Calculate the amount of charge of my battery. Amount of charge in coulombs, right? Of my battery. Here you go. My battery. My battery has a charge of 2,600 milliamp hour. Calculate the amount of charge in coulombs of my battery. Right? Think a little bit about that. I'm gonna write that down, solution here. I'll give you 1 or 2 minutes. Try to figure out on your own and see if you get the right answer, right? This is just a matter of doing some math. In my battery. While you do that, I'm going to get my favorite software here. Nope, not what I want. This one here. Live mass. One minute. Let another minute go by, and then I'll start solving this. It's an exercise, right? Exercise. Don't forget that this guy here is coulombs per second, right? While we are trying to solve your problem, let's see if we can find another battery. Batteries. Okay, you have a bunch of batteries here. Let's see if they have a power. Yeah. Okay, here you go. This is a 12-volt battery. And this one, where is the charge of the battery? I saw it somewhere. 150 amps hour, right? This battery has a charge of 150 amp hour compared to my own battery, smaller cell, 2.6 amp hour. This one is almost 100 times, has almost 100 times more charge than my battery. 2 minutes and 50 seconds. Let's do it. Let's solve that. Almost 3 minutes. Now I'm going to solve that for you. Here goes step by step. 2,600 milliamp hour. Okay. 1 milli is 10 to minus 3. My amp is coulombs per second. And 1 hour is 3,600 seconds. And now you can solve the problem. Start with this one. No. A, S, good. I'll put this right in here. Substitute for M milli, M for milli, right? Amps for coulombs per second, and hours for seconds. Oh, what did I get here? It's 9,360 coulombs. When this battery is fully charged, the top of the battery is going to have plus 9,360 coulombs, and the bottom will have minus 9,360 coulombs of charge. That's what it is. Copy, and I'm going to paste that in my notes solution like that. Okay. 938. That's the idea of current. We have electromotive force. Okay, the battery here you go. The same thing that I did. The surface, the cross section, delta Q over delta T. Okay. Here you go. The device. You can have a device there too. Those are the electrons are powering the device. What else do you have to know? That is one important thing that sometimes make life a little bit confusing. Okay. Some time ago, back in the time of Benjamin Franklin, he used to study those circuits as well. People thought that it was the positive charges that were responsible for the current, okay, at that time. And then because of that, you know, they adopted the current flow in a circuit as going from the negative of the battery to the positive, right? they adopt this direction of the current because they thought it was the positive charges that were responsible for current. Unfortunately, the idea is stuck and nobody did anything to change this convention, okay? So instead of adopting the flow of the electrons as the direction of the current, they adopted the flow of the protons as the direction of the current. And even today we do that, okay? See the electrons is going from the left to the right, huh? Right? Whereas the convention today is the current is from the right to the left. So that's the direction of the flow of the current. Electrons moving to the right, the current is indicated as going to the left in the opposite direction of the flow of the electrons. What else do you have there? Okay. Notes here. The flow of the current is said to be in the direction of motion of a positively charged particle. Positively charged particle. For historical reasons, okay? And nobody bothered correcting that. Even today in the 20th century, we still say that the flow of the current is the direction of motion of the positive particles instead of the negative particles. This is historical incongruence. Going back to your book here. Okay, we gotta talk about something else now. Lots of things to remember, right? Electric current. And there's something else called electric resistance. Okay? If we have electric charge, I'm going to put here at the top electric charge, electric current, and then we have something else new called electric resistance. Yeah. That, by the way, this multimeter here that I showed to you before, not only is capable of measuring voltage, but it's also capable of measuring current, and it's capable of measuring resistance as well. That's why it's called a multimeter. Okay. Voltage, current, resistance. And what is resistance? Okay. The best way to define resistance, electric resistance, is the counterpart. Instead of electric resistance, here you go. Resistance is the electric counterpart of the mechanical friction. Like the name says, it opposes resistance to the motion of electrons. Resistance applies electric resistance applies resistance, applies friction, right? Let's put it this way, applied resistance to the motion of charges, okay? As you may already have inferred, okay, conductors have lower resistances compared to dielectrics, right? because conductors allow charges to move more freely. It means that their resistance are smaller than the resistance of dielectric materials. So here's an illustration of the motion of my electrons. I have my electric force pulling the electrons to the right, but then because of non-uniformities in your copper, and on the top of that, the attraction, the electrostatic attraction of protons of the nucleus in my copper wire, there will also be a resistance force. And this resistance force is almost the same as the electrical force, resulting in a net force equal to 0. A net force equal to 0 means that the electron is going to be either at rest or moving with constant velocity, right? According to Newton's law. And those electrons, they do moving with constant velocity. Their velocity is around, centimeters per second, on the order of centimeters per second, 2, 3, 4 centimeters per second. They're very slow. People have calculated that. Here's an illustration of my copper wire with known uniformities. Known uniformities that slow down the motion of the electrons. Okay. Here go another. Let's see. Let me give you a better picture, a more realistic picture. Okay, the electrons, they don't move in a straight line here in the copper wire. Okay, that's not exactly what happens. The electrons moves in a constant velocity from the left to the right as an average. That's what this motion is all about. An average motion of the electrons is constant from the left to the right. But in reality, what does it do? How does the electron move? They move in a zigzaggy way, like that. The instantaneous velocity is very high, but the overall velocity is that of centimeters per second, like a pinball in a pinball machine, right? That's the best. That's a more realistic model of the motion of electrons. On the average, it's moving at centimeters per second, even though the instantaneous velocity can be very high. Okay, and now we're ready to explain the idea of resistance. Think about that. You have all these non-uniformities, this junk in the bulk of the copper cable. If you get a longer cable, you're going to have more material resisting the motion of the electrons, right? If you shorten your cable, you're going to have less material resisting the motion of the electrons. See, what you see here is the same copper cable that you have here, but cut in half. From this analysis, it's rather, logical to convince, to understand that the resistance is proportional to the length of the cable. Okay. Then we have something else. What about the area? The larger the area, the larger the probability that you're going to have more electrons flowing through this copper cable. What we're doing here is just let's say, a qualitative understanding of where the resistance comes from, right? So not only the resistance is directly proportional to the length of the material, but it is inversely proportional to the cross-sectional area of the material. The larger the area, the lower the resistance. Okay? And then we can come up with an equation. Okay. It's logical, right? You can even think of the motion of the electrons as cars in a freeway, right? It's logical to think that the longer the wire, the larger the resistance to motion of an electron. In other words, we have a relation just like that. Resistance is not an equality, it is a proportionality. Resistance increases with the length. On the other hand, if you get a cable made of the same material, but with a larger diameter, you will allow to have more electrons moving through the cross section of the material. Okay. What does it mean? It means that the resistance is 1 divided by the cross-sectional area of the material. For some reason, I put a prime in that drawing. Yeah, I'll take it out for now. If it's necessary, I put it back. So, if you want an equation for the resistance, it's going to be something like that. Depend on the length, depend on the cross-sectional area of the material. But then it depends on something else too. You saw in that table, Wikipedia table, that the conductivity of the material changes with the material, right? Silver has a conductivity, copper has a conductivity. And by the way, look what this table has here. There's something else called resistivity. Have you thought about that? There's a relation between conductivity and resistivity. Why don't you try to figure out what's the relation between those two numbers that you see here? Can you picture that? Think about that, get your calculator and try one of the easiest relations that you have, that you may come to your mind, right? I'll give you a little bit of time. Get the conductivity and see the numerical value of the conductivity and see if it's somehow you can get this number here for the resistivity. Okay. I'm going to give you the answer now. If you take the inverse of this number here, you're going to get exactly this number. Okay. So conductivity, which in this case they're using the symbol sigma. Okay. Conductivity or resistivity is a function of the type of material, right? So one is equal to the inverse of the other. Okay, it's like that. Sigma is equal to, is not the equality, 1 divided by rho, like that. And now we can realize that the proportionality constant here for the resistance is going to be what? It's going to be a function of the resistivity. That's the actual relationship for resistance, resistivity, the length of the conducting wire, and the, oh yeah, I have to put A prime, right? Why do I have to put A prime? Because A we use for the amps. Okay, that's why I want to distinguish amps from area. So let's put A prime here for the area. Okay, that's the relationship that you have in mind. So the resistance, the electrical resistance depends only of three parameters: the geometrical parameters of the wire and a parameter that depends on the intrinsic property of the wire. Okay, the resistivity is a parameter that depends on the intrinsic property of the wire. In other words, which metal it is made of. It is made of. Which substance? Let's put it this way: which substance it is made of. That's where the resistivity comes from. Okay, just to 956, right? Let's see. Well, get my E07 raster here. No, E07. Here you go. Raster. Good. Is the lab. Today is the 6th. Insert. But before we go, I'm going to prove to you that the resistivity is equal to the inverse of the conductivity. Okay, let's get my first one here. 6.3 times 10 to 7, right? See, 1 divided by 6.3 times 10 to the 7. What do we get? 1.587 times 10 to minus 8. That's what we have here. 1.587. 587 is 59, right? Times 10 to minus 8. Okay. And you can do that for the rest too. 1 divided by that is approximately 1 divided by 6. 1 divided by 6 is approximately, 0.16, right? 0.16. If you want to put it 1.6, you gotta, here it's going to be minus 10 to minus 7. If you want to put 1.6, it's going to be 10 to minus 7, becomes 10 to minus 8, and so on. You can do for everyone here. Let's see another one that's easier to look at that. Okay, here is 4.8. It's almost 5. 1 divided by 5 is 0.2, right? That's exactly what we have here. It's 0.2. A little bit more because this one here is not 5. 4.8. You go 4.4. 0.33 to 0.4. Then you take the inverse of that, you get those two values, and so on. 515, 959 right now. Okay, let's take attendance. Today's the 6th of March. Randy, are you there, Randy?
Yeah, I'm here.
Thank you, Randy. Next, Vanessa Bonilla. Okay, thank you, Vanessa. Ashley Diaz. It looks like Ashley is here, right? Natalie Spinoza.
I'm here.
Thank you, Natalie. Janet Garcia.
I'm here.
Thank you, Janet. Noor Hassan. Are you there, Noor? Okay, further, just type there in the box. Okay, next is Blanca Hernandez.
Here.
Thank you, Blanca. Kaylee Hernandez. I don't see Kaylee here. Joshua Jimenez. I don't see Joshua here either. Okay. Alondra Lima.
Present.
Thank you. For those who arrived late, okay, I decided to postpone the quiz for next week, so you can concentrate on the exam on Monday. On Monday, no, on Wednesday, exam on Wednesday. Kennedy is there, right? Kennedy?
Yes, sir.
Okay, thank you. Daisy Mariscal. Thank you, Daisy. Yesenia Montes Rodriguez. Thank you. Ryan Ong. Thank you, Artur Pacheco. Thank you, Lebilud. Thank you, Donia.
Here.
Thank you, Donia. Elika Pate.
Here.
Thank you, Brianna Valencia. Thank you, and Justina Youssef. Justina here. I don't see Justina. Oh, Justina is coming. Justina, are you there? I'm taking attendance, Justina. Can you hear me? Okay. Okay, thank you. Now we have, okay, good, we're in good shape here. The only student who did answer was Noor. Noor, are you there? Okay, I'll leave this start there for her. And let's have our break. Break from, okay. Okay, thank you, Randy. From 10:02, 10:03 to 10:18 a.m. I see you in 15 minutes. Okay, I'm back here. Oh, here you go. Here we have the idea of resistance. And let's see what's the unit for the resistance. Okay, so I'm going to tell you right now, the unit of resistance can only be
Professor,
determined for some. Oh, yeah, let's. Thank you.
sorry about that.
Yeah, here you go. That's what you want, right?
Yes, please. Thank you.
Okay, thank you. The unit of resistance can only be determined from what we're going to see now, or something else that we're going to see now. That's called Ohm's law. Okay. Ohm's law is not exactly a law, but people call it anyway, because at the time it was very important. Okay. Ohm's law. And I'm going to put between quotes, because it's not exactly a law. It just comes from the fact Ohm's law is derived from the fact that the electric field inside a conducting wire is uniform. Okay? It's possible to derive that, but I'm not going to do that here. If the field is uniform, then the electric potential along the wire is going to be linear. It's going to be linear. It's going to be dependent, right? To be dependent on the length of the wire. Okay? If you get those two together, you find Ohm's law, and that's the one. That's something that you have to memorize. Okay. Remember, it's not a law. That's why I put that in quotes. So Ohm's law relates the electric potential and with the current and the resistance. And from this law here, so-called law, we can find out what's going to be the unit of resistance. Okay. So V equal to Ri. What does it exactly mean? Okay. So the way the thing it means is, if you have a resistor. Here's the symbol for a resistor. At this point, you already saw that the symbol of the battery, right? So, electromotive force. So if you have a circuit, there's a simple circuit that you're going to see out there in your life. A battery, a resistor, and some wires connecting the resistor to the source of electromotive force. Here I'm V, I put V, here I put R. This is a battery that has a very high voltage. The negative electrode is kept under 0 volts. The positive electrode is 120 volts. So it's a battery of 120 volts. I never see a battery like that. No? I have seen batteries of 12 volts. I have seen batteries of 24 volts. You know, here's just an example that I got from a book, okay? But if you want to create a battery of 120 volts, all you have to do is to get 10 batteries of 12 volts and connect them properly. If you connect them properly, you can get all those 10 batteries of 12 volts to behave like a single battery of 120 volts. Okay, so what that exactly Ohm's law states? Ohm's law states when you have a circuit like that, those wires, you know, are thought to have negligible resistance. This wire here and this wire here is thought to have resistance equal to 0, negligible, and that works pretty well in real life. Okay, So it's just like my probe, just like the probe of my multimeter. Let me stop sharing here. And I'm going to unblur my background. Here you go. It's just those wires here for my multimeter, the probe of my multimeter. Okay. When I connect those wires of the probe of my multimeter, those wires behave as though they have negligible resistance. Okay. You still have some resistance in there, but it's negligible compared to the resistance of the circuit itself. And here's the same situation. Here's in the drawings the same situation. Okay? So here's the symbol for a power source. Here's the symbol for a resistor. And here's the symbol for a wire of negligible resistance. So where does the Ohm's law apply? Ohm's law applies right in here. Okay? When the electrons go through this wire, through this resistance, they lose potential energy. Okay, and the amount of potential energy that they lose can be calculated from that relationship that you saw, R times I. Okay, so the electrons lose electric potential, which is given by R times I. Multiply that by the charge of the electron, you get the amount of energy that it loses. Make sense? Okay. That's what you have to have in mind. Now that we have from the above equation, we can determine the unit of resistance. How do we do that? We already know, resistance is V divided by I. The unit of resistance is the unit of voltage divided by the unit of current. The unit of voltage is the volts, and the unit of current is the ampere. Okay, this unit appears so frequently in physics, that we give it a name. We call it Ohm. That's why it's called Ohm's law. And the Ohm is represented by the capital letter, Greek letter omega, the last letter of the Greek alphabet. Okay. Now that we have the unit of resistance, we can find out what the unit of resistivity is all about. Right? So here you go. This one is going to be ohm. This one is going to be meter. This one is going to be meter square. And the unit of resistivity we find by solving this equation. We are going to have inverse of the meter here. And just like that article on Wikipedia said, the unit of resistivity is going to be ohm meter. Let's go. Let's take a look there. This one, what is my article on Wikipedia here? Oh yeah, here you go. My Wikipedia article is here. Ohm meter. Okay. The unit of conductivity is Siemens per meter. Siemens per meter, okay? Which, by the way, is 1 divided by ohm meter. Siemens is the inverse of ohm. And that's what we have. Not this one here, I want. Right, that's Ohm's law. And let's do let's do this example here. Simplify Ohm's law. The filament in a light bulb is a resistor in the form of a thin piece of wire. The wire becomes hot enough to emit light because of the current. Okay, remember that those electrons, they have some resistance going on there inside the copper wire. And that resistance or that friction generates heat. Okay, that potential energy of the electrons, they lose to heat. And the heat becomes so intense in the wire that the temperature of the wire increases. As the temperature of the wire increases, the wires start to glow. That's how that's the principle of the light bulb. Okay, that's what we call the incandescent light bulb. It's called incandescent because the wire is so hot, but so hot that it starts to glow in the visible. In order to ensure that the device remains reliable, right? In order to ensure that the light bulb remains reliable for a long period of time, what do? They encapsulate this wire in a glass bulb. Okay, not only they encapsulate the wire in a glass bulb, but they also extract the air, the oxygen from this volume. In principle, you could have a light bulb working outside this encapsulator, this glass encapsulator, but it's not gonna last very long. It's not gonna last very long because the oxygen in the atmosphere is going to corrode, is going to combine with the hot filament. Okay, the oxygen in the atmosphere is going to oxidate the wire. So that was the, that was the realization of the earlier inventors. How can we, Thomas Edison, for instance, how do you make a filament that lasts long enough, right? Well, they figured out that the best way to do that was not to keep the filament in air, in oxygen, right, in the atmosphere, but to insulate it from the oxygen, encapsulate it in a glass bulb, and extract all the oxygen from inside. And the filament is going to last longer. Here you go. The filament in a light bulb is a resistor, but in the form of a thin piece of wire. The wire becomes hot enough to emit light because of the current. Show figure 20.5. This one right in here, right? Shows a flashlight that uses two 1.5 volt battery. Effectively, a single 3-volt battery. So if you combine batteries in series, okay, you can increase the electric potential difference. That's why some devices has more than 2 batteries, right? Let's see. Okay, here you go. Here's my remote. My remote here has 2 batteries, 2 1.5 volt batteries, and they're connected in series. What does it mean be connected in series? It means that you connect the positive of one battery with the negative of the other one. Like that. If you connect them like that, positive with the negative, and that's exactly what that support is all about, is connecting those batteries like that. It's okay. You double the voltage, the electric potential difference. Do you remember that other battery that I showed to you had 2,600 milliamps? This one has less. I'm going to stop sharing here. This one has less. This one has 1,000 milliamp hour. Okay, because it's smaller, right? It's a smaller cell. And that's what this figure is all about. You want to increase the electromotive force. If you want to increase the electromotive force, you can connect one battery in series with another one after the other. If I connect on the other way, instead of negative with positive, right? Suppose I make the mistake of connecting my batteries like that, positive with positive. Then what happens? You're going to produce 0 volts of electromotive force, okay? Because this battery here is going to act, is going to push in one direction. This other battery is going to push in the other direction. You're going to push the electric charges, push or pull, let's see. Yeah, push the electrons on the other direction. It's going to have a net electromotive force of 0. Okay, so what does he ask you? What is he asking? Let's see. Determine, okay. The current is 0.4 amps in the filament. Determine the resistance of the glowing filament. Okay, 0.4 amps, by the way, is a relatively high current. 0.4 amps is cannot kill you. Okay, in order for a current to kill you, it has to be around 1 amp. That is already almost half of an amp. But circuits in general is going to be 10 times less than that. It's going to be more like 0.04 amps, 0.03. I work with circuits that in the range of 0.01 to 0.03. Rarely I go above that, 0.03. Especially with LEDs. LEDs consume very little current. So let's, all you gotta do here is to use Ohm's law, okay? So I'm gonna go again back to my favorite computer program right here. V equal to R times I. We want to know what is the resistance of the light bulb. Okay. User predefined, user defined. Okay, good. The voltage provided is going to be 3 volts. The current, like I mentioned before, is relatively high current, 0.4 amps. Just a matter of substituting the numeric values here. Current. I'm getting 7.5 ohms, right? V over A, volt over ampere is omega. No. Okay, it's omega. So my resistance is 7.5 ohms. Resistors you can buy out there. There are all sorts of resistors. Nowadays, those things are mass manufactured. They are very cheap if you buy in quantities. Let's take a look at how resistors are sold out there. Unfortunately, I don't have my electronic lab here anymore. Okay, I didn't bring my electronic lab here to Brazil. So, but we can go here, resistors. You already saw how capacitors look like, right? Resistors. Oh yeah, here you go. That's how they look like. Okay, that's how they look like. Little devices like that. You have this wire that you connect to your circuit, and you have another wire. All these colors that you see here in the resistor tells you what's the value of the resistance of the device. Okay, you go to Wikipedia, you go. Remember that I told you, right? There are 4 basic devices in electronics and electricity. Let's go back to our. Just recall that there are 4 basic devices in electricity. One, capacitor, resistor, inductor, and the transistor. Okay. The most recent one is the transistor, which was a 20th century invention. We have seen capacitors already. We have seen resistors already. Further down, we're gonna look at the inductors. Transistors is for a more advanced course. You know, physics of the 20th century. We leave it for more advanced courses, right? Let's take a look at transistor anyway. When it was invented. Here you go, transistor is a semiconductor device. Remember I told you that there are conductors and dielectric devices. There are semiconductor devices as well. That's anywhere between the conductor and dielectric. It's a little bit more complicated. Okay, to amplify or switch electrical signals and power. That's how a transistor looks like. 3 legs. Okay. What about the history? I'm interested in the history here. The thermoionic triode, a vacuum tube invented in 1907. The vacuum tube enabled amplified radio technology and long distance telephony. The triode, however, was a fragile device that consumed a substantial amount of power. Okay, in 1909, physicist William Eccles discovered a crystal diode oscillator. Physicist Julius Edgar Lingfield filed a patent for a field effect transistor. Okay, so this guy filed a patent in Canada in 1925, which was intended to be a solid state replacement for the triode. The triode, which was the vacuum tube. Oh, here you go. That's how the vacuum tube. No, that's not this one here. I wish we had a picture of the vacuum tube here. Let's see. Yeah, I have got the first working transistor. So 1925 is the invention, but it was not possible to actually construct. Proposed. No, he proposed. He didn't invent. He proposed. Okay, he proposed the concept of field effect transistor. That's what usually happens in science. Okay, we envision a device, but we cannot build at the moment because there's not enough technology to do that. The first working device to be built was a point contact transistor invented in 1947 by John Bardeen and Walter Brattain while working for William Shockley at Bell Labs. You know, Bell Labs has a huge history. Unfortunately, they dismantled Bell Labs. I used to have a friend that used to work at Bell Labs. When they started dismantling Bell Labs, he moved to California. And then he called me to work with him there in Torrance. The 3 shared, that's how important the transistor was. The 3 shared the 1956 Nobel Prize in physics for their achievement. So the device was proposed in 1926, and the Bell Lab researchers demonstrated the first point contact transistor. Okay. And the invention was so important that they won the Nobel Prize in Physics for their achievement. So every electronic device has transistors, inductors, resistors, and capacitors in there. If you show me a circuit, I can identify a capacitor there in your circuit. Unless the capacitor is too small and we cannot see, okay? Let's take a look at the circuit board of a cell phone. Maybe we can circuit board of a cell phone. Let's see a picture, right? PCB assembly. Nowadays, they integrate all those devices in a very small scale inside the microchips. Let's see here. Basic component, how it works. Let's see. I'm not going to spend too much time here. If I find one, I'll let you know. What you see here is, oh, here you go. I think I can, no, we cannot identify resistor. Maybe this one a resistor here. Maybe. Okay. But what we have each of those components here have a bunch of capacitor resistors and transistors there. Okay. And that's one example that we came up with. Here you go. Okay, 7.5 ohms. Okay, what we have here, we have here a switch. It's very similar to the switches that we have at home. Let me draw that for you, how we usually draw a switch in a circuit. Okay, switches, we draw them like the following. That's the symbol of a switch. You know, here the switch is open, and then here the switch is closed. Open and close. When the switch is open, the charges don't flow. They cannot jump from this end of the wire to the other end, okay? And then the current is zero. It's the same as to say that the resistance between those 2 points is very large or infinite. The voltage is 120. Yeah, the voltage remains 120, but the current in this case of an open circuit is going to be zero because the resistance is too high. Remember, we have a dielectric between this conductor, this, and this other conductor. We have air between those 2 points. And that's what switches do. The switches turn on and off the current in a circuit. You close the switch, you let the current flow. You allow the current to flow. Here is the case of a circuit with 2 resistors. Okay? Here's the case of a circuit with 2 resistors. And you should know how to treat this type of circuits. Let's see if we have a similar example here. Yeah, I don't think we have it. Yeah, we're not going to do this one. Okay, so let's treat this one here. Okay, circuit, what we have to know. One, circuit with a single resistor. Okay, given the resistance R of the resistor and the electric potential V of an electromotive force, right? Find the current. Find the current, okay? So the solution, we did something similar, right? But we are finding the resistance instead. Right? Find the current. The current, in this case, we use Ohm's law. V divided by R. Okay, yeah. If I don't give you any numerical value, that's how you come up with your answer. V over R. That's how you come up with your answer, right? Of a source of electromotive force, find the current. Now, 2 given a circuit with not a single resistor, but with two resistors, R1 and R2 connected in series to a source of electric motive force, find the current. Right? So that's another type of problem that you might see. Right? And the situation is just like this one here. Two resistors connected in series, like that. Okay, so now you have to picture what's happening here. Your electric charge, your current is flowing through this wire, right? In this case, it's going to be counterclockwise direction. There is no resistance whatsoever between this point and this point here. And then, your charges have some potential energy up to this point. They didn't lose any potential energy whatsoever. And then it goes inside the resistor. Inside the resistor, start to lose electric potential. And you lose electric potential according to Ohm's law. Okay, so across this resistor, the charges are going to lose electric potential. It's going to be equal to V equal to R1I. Okay, and then it's going to pass through this wire with negligible resistance, and then it's going to lose more electric potential from this other resistor. So it loses electric potential. The amount of energy that it loses by passing through these two wires, these two resistors, is going to be, R1I plus R2I. Okay. The current's always the same in this type of circuit. Always the same, because the energy that's being given to the particles is the same. The current remains the same, but the electric potential of the particle is going to be given by those two resistors. That's all you have to have in mind. Okay. Lost electric potential across this resistor, R1I. Lost electric potential across this other resistor, R2I. I'm going to do that in writing very soon, okay? The sum of the energy, electric potential that loses through this resistor and this other resistor must be equal to this other one because of energy conservation. Okay. So let's write it down here. Let's go back. And then we're going to see another example to solution. Okay. Looking at the circuit, I'm going to copy that and paste so you can have that in the notes. My notes. Okay, the situation is like that. Look at the circuit. The charges move from the positive terminal to the beginning. That's how you should, to the beginning of the first resistor, without losing any potential energy whatsoever, because the wires, these wires, have negligible resistance. Okay. Once the charges get to the first resistor, comma, they will lose, right? They will lose once the charge get to the first resistor and move across it, they will lose electric potential energy due to the resistance. The electric potential they lose is given by Ohm's law. So here we go. Gonna be something like that. V1 equal to R1I. What I have to tell you too is that I'm going to even be a little bit more, I'm going to put I1. Let's say, the current here is different from here. You're going to see that it's not going to be different. Okay. After passing through the second resistor, the charges will lose an additional electric potential. Okay, and this electric potential is going to be given. So let's say here you go, V2 equal to R2 times R1, times I1, like that. Two important things. Two important things. Okay. One, the electric potential between those 2 points is exactly the same as the electric potential between those 2 points due to conservation of energy. Okay. Let's put it this way, due to conservation of energy, okay, we must have the following. D equal to D1, one more, D1 plus, plus V2. Okay. You must have this also, because this is a single closed loop, okay? The current throughout, the current along the whole circuit must be the same elsewhere, everywhere, must be the same everywhere. So that's where we get more.
Professor?
Yeah.
I know a lot of our classmates just got kicked out of the Zoom. I know I was.
Really?
Yeah, I was, but
I don't
I
know why.
auto reconnected, and then some people have to rejoin. So I don't know what happened, but I just wanted to let you know.
Yeah,
Oh, thank you. Thank you for
that
letting me
just
know.
happened randomly. I don't know what happened.
Yeah,
either.
for some reason Zoom keeps on kicking us out. This is the third time I'm getting kicked out.
Oh, I'm sorry.
This was the
I
first
don't know
time that
why.
happened to me.
Really?
Just now. Yeah, it just it kicked me out of the class, but it connected back on its own.
Uh-huh. Okay, one more. See, one more student here. Yeah, I noticed a lot of students are coming back now. Let's see. Let's wait a little bit. Let's see. Admit, Janet. Where did, okay, up to which point were you following? What did you miss in this interim? Can you hear me?
Yeah, I mean, personally, I didn't really miss anything, but my Zoom, it took
Uh-huh.
maybe like a few seconds, maybe 5 at most, for me to
Uh-huh.
get back in. So I don't think I missed anything.
Okay.
But other people, I know they were
I
kicked
didn't
out for
miss
longer.
much either. It was, yeah, it
Mhm.
was the same amount of time for me as her.
Uh-huh. That must be something. It looks like something in Zoom, right? Here I have electricity. Okay, if the electricity goes down here in my place, sometimes it happens, right? I have a no break system, and we won't have any problems, any interruptions whatsoever. Last semester, I had what, 2 or 3 times, right, that I got without electricity here, and then I managed to get this device that allows me to stay connected when the light goes off here in my place. So I do not know. It seems to me that is a problem there is Zoom.
Professor, I think we just want to make sure that as long as it was still on for you, that the class was being recorded. So like we wanted to let you know that we were being kicked out, but as long as it's still recorded, then it should be fine. We just thought
Okay.
that the meeting had ended on their end for a second.
Yeah, I didn't do anything here on my side, so thank you for letting me know. Let's see, we have 13 students. What time is that? 11:02. It's time for a break, right? But
Yeah.
let's finish this example. Let's finish the example, and then Jeanette's trying to log in. Okay, so here we go. Now that we have here, V, V is going to be V1 times V1 plus V2, right? V1 is going to be this one. V2 is going to be this one. And let's see, also because this is a single loop, closed loop, the current along the circle must be the same everywhere. And then what we're going to have, that I1 is going to be equal to I2. I1 is equal to I2, which, by the way, I'm going to write down as being I. Okay. And when we have that, I will replace I1 and I2 with I. And now we can solve this problem for the current. It's going to be I is equal to V over R1 plus R2. Okay. Let me see. Okay. So that's what we get. What you see writing here, I'm going to write that down in a different way as well. I'm going to write that down. The I as the I being factored here. R1 plus R2 times I. What you see here is what we call the equivalent resistance. For this circuit, for this circuit, R1 plus R2 is the equivalent circuit, equivalent resistance. So by the same token that batteries connected in series, result in electrical motive force equal to the sum of the two separately, we have the same for resistors. Okay. So going back here to my drawing here, we can solve this type of problem by combining those two resistors in a single resistor. This single resistor here has an equivalent resistance of R1 plus R2. And by the way, we see that very frequently in the lab. It works pretty well. Okay. And the current don't change. Okay, so in circuits, so let's summarize here. In circuits, with elements connected with resistors, right? Connected in series. Circuits with resistors connected in series, okay, can be reduced to a circuit with a single equivalent resistor given by the sum of the separate resistors. Okay. So that's the case of circuits in resistance. If there is a resistivity, we covered that. Okay, here is a device called the plethysmographer, right? That measure the impedance. They call it the impedance, which is something very close to that of a resistance. Okay, impedance we're going to see later on. We're not going to cover that. Don't worry about that. It shows that the resistivity depends on the temperature. We are not going to talk about that. Let's see. We go a problem with the resistivity, electric power. Let's talk about electric power now. 1108. Okay, before we talk to electric power, let's take a break, right? 1108 already. And so we cover electromotive force and current, Ohm's law, resistance and resistivity. Wow, they're bunching up everything. They have finally here series wiring and parallel wiring. Okay, we usually talk about this one later on. Okay, so I'm going to skip this one. I already talked about the series wiring, and then I'm going to talk about parallel wiring. Okay, so far the chapters that we covered are 20.1, 20.2, 20.3. I already got 20.6. Series wire partially in series and partially in parallel. Okay. Internal resistance, the measurement of current and the voltage. Oh, he's covering capacitors in series and parallel. And now we're going to cover capacitors in series and parallel too. Okay. So that's what we cover so far. 1, 2, 3, and 6. 1, 2, 3. We didn't cover electric power yet, and 6. So what I want to do, next 20.7, 20.8. I'm not going to adopt the order of the book. And then we can do 20.12 as well. Okay. Okay, and now let's go for a break. 11:10 to 11:25 a.m. Okay. So any questions? Everything is stabilized there with your connection or Zoom connection? I hope so, right? So let's go for our break and I'll be back shortly. See you in 15 minutes. Okay. I'm back here. Okay.
Professor.
Yeah.
So for the exam, we'll still focus on chapters 18 through 19 in what you outlined in the last class?
Yeah.
Okay, thank you.
And don't forget lab 1 too, right?
Yes, sir.
Let's take a look again. So let's see, material for the first exam. Yeah. Yeah, plus lab 1. Okay. Yeah, the sections, right, are listed here. Material of those chapters. And of course the related, related notes and related notes. Okay, so that's one type of circuit. Let's figure. I'm gonna summarize again. A summary: electric charges, right? Electric force, electric field, electric potential energy, electric potential. And after that, electric circuits. Electric circuits. Oh, wait a minute. Now, before that, there's going to be electric current, right? Electric resistance, including resistivity, and electric circuit, right? And then circuit in series and circuit in parallel. That's what we're going to deal with. What we're talking about is that what electric circuit, let's put like that first. DC's, DC stands for direct current circuit. Okay. Circuit in series, circuit in parallel. So there are two different circuits, electric circuit. There is the direct current circuit, and then there is the alternate current circuit. We usually cover the direct current circuit DC, right? First. And we talk about circuit in series, circuit in parallel. And then you have a mixture. How do you say? The book has a good way of mentioning that. Circuits wire partially in series and partially in parallel. A combination, right? Combination in series and parallel. Good. Running out of space here in my page. Oh no. Okay, that's good. Yeah, good. Circuit in series. circuit in parallel. Combination in series and parallel. Combination series and parallel. Let's do it this way, otherwise I'm going to run out of space. Let the circuit DC. Circuit in series, circuit in parallel. Combination in series and parallel. Okay, that's how it goes. And going back here. Okay. In a circuit in series. In a circuit with elements in series, okay? It doesn't have to be resistors alone, it can be other devices as well. In a circuit with elements in series, the electric potential sums among the elements until it is equal until it is equal to the potential provided by the electromotive force. Okay. Also in circuits in series. In circuit in series, the current is the same along the elements. In a circuit with elements in series, the current is the same along the elements. Okay, so we have this characteristic in the case of elements connected in series. Important characteristic, and it's going to become intuitive when we start talking about elements connected in parallel. It's going to become more intuitive. Okay. I'm going to start putting together a table here for you so you can visualize it better. Insert table. Okay. Circuit. Series. Voltage. I'll put another line here. The other line is going to be for parallel. Okay, we didn't cover parallels yet. V1 plus V2 is equal to V, like that. V1 plus V2 is equal to V. That's two elements, right? You can have n elements if you want. The voltage, the current. I1 equal to I2 equal to I. And And by the way, it doesn't have to be as 2 elements, it can be more elements. I1 equal to I2. Well, equal to, here you go, equal to I. Your current. But let's not worry, don't forget that for resistors, we are going to have another one for capacitors, okay? We can have capacitors connected in series and parallel in a circuit as well. And we can, just like I said, you can have more than one element. We can have more than one element. Suppose that we have n elements in series, right? And like that, current. Okay, what else? What else I have to know? I'm gonna put another table here for you. The equivalent resistance in a circuit with n resistors in series is going to be what? R1 plus R2 plus Rn, which is going to be equal to summation I equal from 1 to n Ri. It's going to be like that. That's the representation. Now let's talk about the resistors in parallel now. Resistors in parallel now. They look just like they look just like the way I said. We have 2 resistors, one in parallel with the other. They're not one after the other. Those are the 2 important types of connections that we have between elements. And then you can have a combination of series and parallel as well. Okay, in this specific case, something different happens. Okay, in the case of the circuit in series, the current just flows through a single circuit, through a single branch. Yeah, and through a single circuit, right? Because you have just one circuit. In this case, you're going to have 2 circuits. We're going to have this circuit here, and we're going to have the second circuit as well. Okay. The analogy for cars and freeways is that of a fork at the intersection. Think about that. Your car is moving, your bunch of cars, right, is moving through the circuit. When it gets to this junction here, and we call it junction, a circuit junction, some of the cars flows in this direction, some of the cars flows in the other direction. The amount of cars or the amount of charges that flow in this direction depends on the relative resistance of this one with respect to this other one. If this resistance is greater than this one, then you have we have a smaller current, less flow, because you have more resistance. If you have a lower resistance, there will be a larger current flowing here in this branch. Okay, and then here R1 and R2, the same drawing but in a different orientation, right? So here you go. Current flowing. See what happens here? The current is split. You have this main current flowing here. A little bit of this main current goes in this direction, and a little bit of the other current goes in the other direction. Now the current is no longer the same. The current is split. Okay? And I1 plus I2, due to conservation of charge, I1 plus I2 must be equal to I. Okay? Because those two resistors are connected in parallel to the source of energy, the electric potential across it is going to be the same as that of the battery. Here too. Okay? That's the main difference between circuits and elements in series and elements in parallel. It applies whether it's for a resistor or whether it's for a capacitor. Let's compare in the table how it looks like. Okay, voltage. Voltage is the same. Okay, it's going to be this thing here. Like it's complementary. We say that one complements the other. V1 is equal to V2 equal to Vn equal to V. Okay, it's going to be equal, not the sum. And the current is going to sum. Is easy enough to memorize? Here you go. I1 plus I2 plus In equal to I, the main current. Okay. For resistors in parallel, because now the relation is different, the equivalent resistance is going to be different as well. Resistors in parallel, the equivalent resistance is going to be something like that. Now it's going to be the inverse. Oh, and it's possible to prove that mathematically. One divided by R2, 1 divided by Rn. And that's what we end up having here. Okay, the summation. Like that. That's one type of circuit, right? Two types of circuit. And when we reduce this branch of the circuit here to an equivalent circuit, what we get? We get this equivalent circuit here. That's going to be, the inverse of that is going to be the sum of the inverses. In the first case, it's the summation of the elements, of the value of the elements. And in the second case is the summation of the inverse of the resistance. Summation of the resistance and summation of the inverse of the resistance. Now, there are some important properties about that I'm going to tell you. Okay, it's possible also to prove when circuits, when elements, when resistors, right? When resistors are connected in series, the equivalent resistance will always be greater than the largest resistance. Okay. So let's say it's possible to prove that because we're summing, right? That's kind of It's kind of intuitive, right? Let's say, you know, Rn Rn is greater than everybody here. Okay. This implies that R equivalent will always be greater than Rn. Resistance, this follows because resistance is always positive. It's always a positive quantity. Okay. Now here's the inverse. Here's the inverse. Think about that. Okay, let's say, let's say R1 less than R2 less than Rn, right? If you have something like that, the same set of resistors, right? The inverse of R1 will be greater than the inverse of R2, right? It's going to be greater than the inverse of Rn. Okay. Okay, so, well, definitely the inverse of the equivalent resistance is going to be greater than the inverse of R1, right? Make sense? I'm summing positive quantities. And what does it mean? It implies that R1, even better, let's see. No, I don't want to put a greater than, it's going to be greater than Rn. Here you go. It's going to be greater than Rn. Let's see, that I want to do that. Yes. Yeah, that's right. That's what I want to do. That's what I want to do. What does it imply? It implies that this, let's see. Yeah, I want to go back to R1. I'm sorry. Here you go. R1 is the smallest of all resistors, right? R1 is the smallest. Before, Rn was the largest of all resistors. Okay, R1 is the smallest of all resistors. Consequently, the inverse of R equivalent is going to be greater than the inverse of R1. Consequently, what's going to be? Is going to be that my equivalent resistance will always be less than the smallest resistance. That's what it means. In the first case, okay, in summary, for resistors in series, the equivalent resistance is larger than the largest resistor. Okay. For resistors in parallel, the equivalent resistance is going to be smaller. Is smaller than the smallest resistor and the largest resistor. And then, okay, we can do some numerical examples here. Let's do some numerical examples. I'm gonna get only 2 resistors, okay? Resistor 1 equal, let's see, 10 ohms. Good. And resistor 2 equal to 100. Now let's put 20 ohms. Right? I will connect them in series. In series. Okay, R1 equivalent R1 plus R2. I'm going to organize it here nicely. Okay. It's 30 ohms. Okay. So the equivalent resistance is greater than the largest resistor of those 2 sets. And what about in parallel? In parallel. In parallel. Here we go. We're gonna have the the inverse, right? The relationship is the summation of the inverse. 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 Oops. And I'm going to replace each value numerically, no matter what the numerical values that you have. What I wrote that down is always gonna be true. Expand. Oh no, you gotta factor it. Collect. Here you go. Good. And now solve. I want to do collect. I want to do like that. And then I want to solve for the equivalent resistance. Okay, that's going to be what? Calculate 6.66. So the equivalent resistance is the smallest of the other 2. And you can do that for 3, 4, 5, 10, 100 resistances. This always will hold. For circuits that are purely in series and for circuits that are purely in parallel. 1153 example, right? Example. Okay. That's what we have, and now we have to combine those 2 different types of configurations, right? Okay, we have here 3 circuits. Oh, here you go. See, the way we solve problems is like that. First we start with the original circuit. We start to, simplify the circuit to a single element. From 3 elements, this one went to 2. Look at the notation that I'm using. Resistor R1, R2, R3. When R1 combined with R2, it gives me an equivalent resistance that I call R12. Okay. When the R12 combined with R3, it gives me an equivalent resistance that's R13, and then we can now solve the problem for current in the circuit. Okay. What about here? We do the same thing. Combine each pair of elements separately. R12, right? R12, and we know that the inverse R12 is the summation of the inverse R1 and R2, and R123. Okay. That's the equivalent resistance. Okay, the current, here you go. The current here, oops. The current comes out of the battery. It splits towards the R1 resistor, towards the R2 resistor, and towards the R3 resistor. Okay. Let's see. There is something wrong here. Okay, it's not plus, it's minus here. Okay. That was, you lost some of the current, right? I minus I1. And then I3 becomes I minus I1 minus I2. Okay, here I3 combines I2. And then we finally have just I. Okay. What time? We have 4 more minutes to go. And then now we have this combination of circuits, right? That's what your book was talking about. We did internal parallel wiring, that's 20.8. Okay, we did 20.7, that's parallel wiring, and what's coming next is the combination. I'm gonna take this one out from here and place it right here. Oh no, it's not what I want. What's going on here? Okay. Okay. We're going to do that now. Now, combination of elements in series and parallel. Okay. So when you have a circuit like that, make sure you can visualize the current. You still do not know what the value of the current. You may know the value of the potential, electric potential, and the resistance, right? Suppose that you want to know the current. You have to do this exercise. You have to visualize the direction of the current. You have to visualize the fact that the current is splits in one branch towards the other. So the main current is called I. This current here I call I1, 2 because I have resistors 1 and 2. And this current here I call I3. Okay. So the first thing that you're going to do, you're going to realize that this resistor is connected in series with the other resistor. Okay. This resistor here is not in parallel with this resistor, nor this resistor. Those two are not in parallel. Those two are not in parallel. What is in parallel is the combination of those two resistors. The combination of those two resistors is in parallel with this one. So when I combine those two in series, I have the R12 here. The R3 is left, and now the R12 is in parallel with R3. Okay, and then you're going to have your R13. And I'm going to write that down. We have 1 more minute to go. Okay. In the example of the notes, now what we have are R12. R12 is equal to R1 plus R2. And now the net R123 resistor is going to be given by the R12 resistor, the inverse of the R12 resistor, and the inverse of the R3 resistor. Like that. Okay, and then you can solve, right? Let's solve that together. Oh, we're running out of, it's already 12. You can finish that on your own, right? Or I can do that in my favorite software. Let's do that. You go. 1 divided by R123 is going to be equal to 1 divided by R12. That's a very good notation, okay? Plus 1 divided by R3, okay? Don't forget that R12 is R1 plus R2 because they're connected in series. R1 plus R2. Almost over. I'll let you go soon. Here you go. And then you solve for R13 in 1, 2, 3 in terms of everybody else. Okay. If you want to simplify, you can simplify. Okay, and get everything in a single fraction. Okay, we run out of time. 12:01 right now. And if you don't have any questions, we can finish here. Okay. Any question? Okay, we have office hours now until 12:45. If you want to stay around, that's okay. Otherwise, I see you Wednesday. Welcome. Thank you, too.
Professor?
Yeah.
Hi, sorry, my camera went out for a second. But our exam is Wednesday at 8:50, correct?
8:50, yeah, 8:50 to 10:50, 2 hours.
Okay, perfect. And
Wednesday.
it's the same link we use for Zoom.
Yes, so you have to be in Canvas, right? And
Yes.
simultaneously you have to be in Zoom as well. with the
Okay, and then
Canvas.
lab 2 is due next Wednesday, correct?
Not the day after tomorrow, but the Wednesday of the next week. Okay.
Wednesday of next week. Okay, thank you so much.
Right. It's gonna be, let's see, 8, 9, 10, 11, 12, 15th, right? The 15th of March.
The 15th of March, yes.
Okay.
Okay, thank you.
Okay. Bye-bye.
Bye.
What's that? Okay.
Professor,
Yes.
it was brought up to my attention that you called roll, and at that time Zoom had kicked me out and I had to come back into, or for some reason I just couldn't see the Zoom screen at all to unmute and say that I was present. So I just wanted to clarify that, but I didn't want to interrupt you. But I
Okay.
was in the Zoom.
Okay, here you go. 1.
All right.
Okay.
Thanks. Thanks a lot.
Welcome.
Take care, Professor.
Is it?